Have you ever driven a car straight down a road and then tried turning at a junction? That switch from straight to turning marks a big leap in how we describe motion, from one-dimensional to two-dimensional. In the last chapter, we looked at motion along a straight line, where direction was easy to handle using plus and minus signs. But once an object starts moving on a curved road or in any direction on a flat surface, signs just aren't enough. Let's say you're playing football. The ball doesn't just move forward or backward, it curves, arcs, and even goes diagonally. That's motion in a plane. And to study such motion correctly, we need a better mathematical language. This is where vectors come in, a powerful tool that lets us define both how much and in which direction something moves. From describing position to calculating velocity and acceleration, vectors help bring precision to the physics of motion in 2 and 3 dimensions. So, what exactly is a vector? Think of it as a quantity that carries two essential pieces of information: its size or magnitude and its direction. Unlike scalars, which are simple values like mass, temperature, or time, vectors are more expressive. They tell us not just how much, but also where to. Displacement, velocity, acceleration, and force, these are all vector quantities. You can't fully describe them without including their direction. Picture wind blowing at 20 kilometers per hour. That number alone isn't enough. You also need to know where it's headed, northeast, southwest. That direction turns it into a vector. In physics, direction is just as important as value. And that's why vectors are essential for exploring the real behavior of moving objects. Let's make this more visual. Imagine a bird flying across a park, not straight, but diagonally. Or a cricket ball soaring after being hit. The motion is happening in a plane, not just along a line. Now, this kind of motion has parts, a horizontal component and a vertical component, and both change with time. Vectors allow us to split these components and analyze each independently. For example, we can break the ball's velocity into two perpendicular directions, horizontal and vertical, and use separate equations to study each. The total motion forms a curved path, but vectors let us treat each axis individually to calculate where and how fast the object is going. Without vectors, we wouldn't be able to predict trajectories or final positions in such curved motion accurately. Where does all this vector talk actually help us? Well, everywhere, from flight paths to video games. Pilots adjust their course based on wind direction and speed, both vectors. Engineers design roller coasters and water slides by analyzing motion curves using vector equations. Even satellites follow curved paths around Earth called orbits. And guess what? Those are classic examples of motion in a plane. Think about how gravity and friction pull in different directions. Only by resolving these forces as vectors can we calculate motion properly. In short, motion in a plane is how real life works, and vectors give us the physics toolkit to understand it. Before we dive deeper, let's preview the mathematics coming your way. You'll soon learn how to add, subtract, and multiply vectors both graphically and analytically. You'll see how a single vector can be split into two perpendicular components. This is called resolution of vectors. For instance, a velocity vector can be split into horizontal and vertical parts. One of the key equations you'll use is acceleration vector equals change in velocity vector divided by time. This means take the final velocity vector, subtract the initial velocity vector, and divide the result by the time taken. You'll see how vectors can be added using the head-to-tail method or triangle law. These techniques help simplify real-world motion into solvable components. Let's quickly recap what we've learned. When motion happens in just one dimension, a plus or minus sign does the job. But in two-dimensional motion, like flying, falling, or curving, direction matters far more. Vectors allow us to include direction in our equations for displacement, velocity, and acceleration. That means we can now study real-world physics, curved paths, changing directions, and combined forces with clarity. You'll soon apply these concepts to projectile motion, where objects move in a curved path under gravity, and to circular motion, where direction keeps changing continuously. So as we move ahead, remember, mastering vectors is your key to understanding motion in a plane. I hope this gives you a solid start to the world beyond straight-line motion. See you in the next session, where we dive into scalars and vectors in more depth.